SOA World, that is SOA Weekly Academic Lecture of today. And let me introduce Dr. Ratan Giri to all our faculty members. Uh, he is an assistant professor at the ITER Institute of Information and Technology, Jaipur, Rajasthan. He completed his MSc from IIT Guwahati in 2012 and his PhD from NIT Rourkela in 2018. After his PhD, Dr. Giri joined Aalto University School of Science, Finland, as a visiting researcher in 2018. He has earned postdoctoral experiences from Aalto University School of Science, Finland, and Technion Israel Institute of Technology, Haifa. His current research expertise includes partial differential equations, functional analysis, etc. He has published around 13 number of research papers in Journal of International Repute so far. He has participated and delivered talks in numerous conferences and workshops. Dr. Giri is a reviewer of scientific journals, Acta Mathematica Scientica, Philomath, Journal of Function Spaces. Dr. Giri qualified CSIR NET in 2017 with All India rate 51, GATE in 2012, and JAM in 2010. He was also offered Merit Cum Main Scholarship 2010 to 12 from IIT Guwahati. So this is we are very much glad to get Dr. Ratan Giri today as a speaker of our 33rd SOAWAL. And today's topic is on the super solutions related to the parabolic p-Laplace equation. So I welcome you, Dr. Ratan Giri. Now you can start your talk. Thank you so much for accepting our invitation.
Yeah, thank you, ma'am, for the introduction and the invitations. It is my great pleasure for me to deliver a lecture at your institute. Okay, so first let me share my screen. Give me a few seconds. Okay. Is my screen showing properly?
Yeah, it's visible.
It is now proper?
Yeah.
Okay. Thank you. Okay, so I'm going to speak about super solutions related to parabolic p-Laplace equation, and the talk will be based on my one of my recent work jointly with Professor Juha Knunen and Christian Morin. So here is the PD, okay, which is basically ut minus delta p of u equal to 0. This PD I call as the parabolic p-Laplace equation. Here p is basically lies between 1 to infinity, and delta p is basically p-Laplace operator, and it is basically given by divergence of mod of gradient u to the power p minus 2 multiplied with gradient u. So if you look at this expression carefully of this p-Laplace operator, for p equal to 2, you will have the usual Laplace operator, what you know from your PDE course. So what the problem what we have considered here, it is nothing but a nonlinear generalization of a heat equation. So for p equal to 2, this parabolic p-Laplace equation is nothing but the heat equation. And this is one of the nonlinear generalization of heat equation. Okay, so here we will talk about solutions and super solution related to this PDE. Okay, and I mainly speak about the classes of super solutions. Although there are several notions of super solution in the literature, here we will consider the notion of weak super solutions, which are defined through stress functions under the integral sign. And secondly, I will speak about p superquadratic functions, which are defined through a parabolic comparison principle. And the main goal of this talk is to discuss a possible connection between these two classes of super solutions. Okay, and moreover, we would like to see what are the SOAWAL space properties of p superquadratic functions. And to keep the things simple, I will not give any proof, only I will discuss the results, and in some cases I may give some idea of proof. Okay, so here is the outline of the talk. So I will start with basically the notion of weak derivative and weak solution of PDEs. Then I will speak about the p-Laplace equation, which is basically given by minus of delta p u equal to 0. Then finally, I will come back to our original equation, parabolic p-Laplace equation. Okay, so let us now start with the notion of weak derivative. Okay, so first of all, why we need such a notion of weak derivative? One of the main reason is that most of the physical problem are nonlinear in nature, and most of them do not possess solution in the usual sense, which I called as in the sense of classical. Okay, for example, the problem what we have considered here, the parabolic p-Laplace equation, it is nonlinear and it does not possess the solution in the classical sense. Therefore, we need some kind of generalizing notion of solution in order to understand the physical phenomena of the problem. So more precisely, in order to allow discontinuous function as a solution of some PDE, the notion of weak derivative and notion of weak solutions were introduced in the literature. And the concept of weak derivative is basically rely upon the integration by parts formula. Basically, if you consider a function f, which is C1 means one times differentiable and derivative is also continuous. And if you consider this integration, okay, f del phi del xi. Now, if you apply the integration by parts formula, then what do you have? You have f phi restricted on the boundary of the domain minus integral over omega del f del xi phi dx. Okay, where phi is basically completely supported smooth function. By means, what I mean to say, the functions are basically infinitely differentiable and having a complex support. Okay, and I call this class of function is basically as a test function space. Okay, and a function belonging to this space I will call as a test function. Okay, now since you know that the function vanishes on the boundary, therefore this integral, this term vanishes. Therefore, you are left with only this equation, integral over f del phi del xi dx equal to this expression. Now, if you should observe here that the derivative of phi has been thrown to the derivative of f by applying the integration by parts formula. This gives us the motivation to define the weak derivative of a function. Now, one important remark here is that in order to define this integral, what do we need? We need function f should be locally integrable. That is enough because the state function phi is basically infinitely differentiable. It has compact support. In other words, the derivatives of phi with respect to xi has a maximum. So we can take out. Therefore, this integral makes sense when f is locally integrable. Therefore, we define the notion of weak derivative for locally integrable function. Okay, so here is the definition. It says that gi will be a weak derivative of locally integrable function f with respect to the variable xi. I should mention here that our domain, what I am considered here is in Rn. Okay, so that is why I am taking here the weak partial derivatives. Okay, so gi is said to be a partial derivative of the function f with respect to the variable xi if this integral equality holds for every test function. Okay, so this is how the notion of weak derivative is defined. Okay, so it will be more clear if we see some simple example. So if we come to the case when n equal to 1, mainly we are in the setup of real line, and you consider your domain is -1, 1 open interval, and you take the function fx which is 0 in the open interval -1, 0, and it is x where in the interval 0, 1. Okay, now you can see that this function is not differentiable at the point origin. Okay, but it has weak derivative, and weak derivative is precisely given by this function gx, which is 0 in the open interval -1, 0, and 1 in the open interval 0, 1. And it can be seen from the following step. Okay, so basically you take a test function And you if you see this integral minus 1 comma 1 f phi prime dx, I can divide this integral into two parts. First part is minus 1 comma 0, and second part is basically 0 comma 1. Okay, now in this domain your function is precisely 0. Okay, so here is basically your function is x. F takes the value x. Okay, so you are left with only integral over 0 to 1 x phi prime dx. Okay, now you apply here the integration by parts formula. So you will have basically x phi restricted on the boundary. So here is the boundary. We have only 2 points basically in this domain 0 comma 1. One is 0 and another one is 1 point. Okay, and minus of integral 0 comma 1 phi dx. Okay, just we have applied the integration by parts formula. Okay, then what you have, you know that phi is compactly supported, therefore phi must vanish on the boundary. In other words, phi at 1 equal to 0 and phi of minus 1 is also equal to 0. So therefore we are left with only this integral minus of 0 comma 1 integral over 0 to 1 phi dx, which we can rewrite as this expression, where g is basically this function. Therefore, by the definition, this function gx is basically the weak derivative of this function fx. Okay, so this is how the basically the weak derivative of a function is basically defined. It's really depend on the integration by parts formula. And similarly, you can see, you can check by your own that mod x, it is not differentiable at origin, but it has weak derivative, basically the step function 1 comma minus 1. Okay, now let me give you the notion of weak derivative of general order. So for that, what we need the multi-index that you know from your PDE course, which is basically a n tuples consisting of natural number together with 0, and its order is basically given by mod of alpha, which is basically the sum of all n tuples. Okay, so here we say that g is the alpha product weak derivative of the function f if this integral equality hold for every state function. Okay, here d alpha phi is basically alpha product partial derivative of phi. Okay, which is basically given in these expressions. Okay, and in particular, if you take mod of alpha equal to 0, you have d0f, which is basically f, and if you take the one order partial derivative, basically df, you have basically gradient, which we call as a weak gradient of the function. Now here is one important question, that is that for a function f, how many weak derivative will exist? Okay, if there exists more than one, then our definition will not make sense. So we need some kind of uniqueness of weak derivative, and the result says that since we know that the space of smooth function having compact support is dense in the locally integrable space, so for a function, if weak derivative exists, then it is unique up to a set of measure 0. Basically, weak derivatives are defined almost everywhere, and they are equal up to a set of measure 0. Okay, and moreover, if the classical derivative for a function exists, then the classical derivative coincide with the weak derivative, but converse not true. Okay, for example, if you consider the characteristics function over the set of rational number, this is already, you know that this is nowhere differentiable, but it has weak derivative 0, because we know that the Lebesgue measure of the set of rational number is 0. Therefore, the notion of weak derivative generalizes the notion of classical derivative in this sense. Okay, now let us talk about the weak solution space of PDEs, which are known as the basically the Sobolev spaces. Basically, it consists of all p integrable functions whose weak derivative exists, and the weak derivative was also in the LP space. Okay, and this Sobolev space is basically a Banach space with respect to this norm, these two norms. Basically, when it's depend on where the p lies, when p lies between 1 to infinity, this is precisely the norm. When p equal to infinity, you have basically essential supremum norm, basically the L infinity norm of the all weak derivatives. Okay, so here basically k is the order of the Sobolev space. So in particular, if you take k equal to 1, then your Sobolev norm will be basically given by this simple expression. What is it? Is basically the sum of LP norm of u and with the weak gradient of LP norm of U. Okay, this is how the Sobolev norm is defined. Okay, and the Sobolev space with zero boundary values is basically the closure of the space of smooth function with respect to this Sobolev norm when your domain is bounded. Okay. Now, basically, let's look at some properties of Sobolev spaces. You already know that for p equal to 2, L2 space is basically Hilbert space, and also you know that when p lies between 1 to infinity, your LP space is basically reflexive, and if p includes 1, then your LP space is basically separable. The same result also true for the case of Sobolev spaces. Okay, so now I'm going to introduce the local Sobolev space, which is defined similarly. Basically, we say that a function u belongs to the local Sobolev space if u belongs to the Sobolev space over omega prime, where omega prime is basically a relative compact subset of omega. Relative compact means its closure is a compact subset of omega. Okay, so like L1, how we define L1 log, it is like the similar fashion. Okay, so this is how these are the Sobolev space properties. For more details, you can look at the books I have written here. So you can, if you are interested in, you can look at these books. Okay. Uh, Now let us talk about the motivation behind the weak solution of a PDE. So for that, let us first consider a simple PDE minus Laplacian u equal to f, okay, where f is a given function, and you know that u is a classical solution of the PDE if u in the class of C2. C2 means u should be 2 times differentiable, and it satisfies this PDE pointwise. Okay. This is the meaning of classical solutions. And you already know the existence of classical solution from your PDE course. It says that if the given function f is smooth enough and compactly supported, then the solution to this PDE, which is basically the classical solution, is basically given by the convolution with f with the fundamental solution phi. Okay, here phi is basically this expression for n equal to 2 and n greater than equal to 3. This is basically the fundamental solution for the Laplace operator. Okay, that you know from your PDE course. Okay, now here is one important question. Here, what we have assumed? We have assumed that f is smooth enough, means f is differentiable, means f is infinitely differentiable and having complex support. In this case, we can guarantee the existence of classical solution. Now, for example, if I take f is some locally integrable function. For example, if you take f is a step function in one variable case, 1, minus 1. Okay. So in this case, does your PDE minus Laplacian u equal to f possess a solution? And answer is no, because of the Darboux theorem. What the Darboux theorem says? It says that derivative functions always have the intermediate value property, right? But the step function do not have the intermediate value property. That is why this problem, when I will consider f as a step function, this problem do not possess any classical solutions. Okay, so therefore we need to define the notion of weak solution. Now, how should we define a weak solution? So what we will do? Basically, we choose a state function from the state function space, and we first multiply the PDE throughout the PDE. Okay. Now we integrate both sides. Now in the left hand side, we will apply the integration by parts formula. So if we apply the integration by parts formula, then we have precisely this expression, which is nothing but the Green's identity. Okay. Now, since you know that the function phi is compactly supported, so phi vanishes on the boundary. Therefore, you are left with only this term. Now you look at the term overall. So here, what do we have? The order of the derivative u here is 2, but here you can see that order of the derivative u is reduced by 1. Okay, that is one important thing. And second thing is that when this integral will define. So basically, if I take u belongs to this local Sobolev space, then by applying the Holder inequality, this integral exists and finite. Basically exists. Similarly, when f is in L2, this integral makes sense. Therefore, we can give the definition of weak solution to this PDE. So here is the definition of weak solution of the PDE. It says that if your given function f is in locally L2 space, we say that u is a solution to this PDE minus Laplace and u equal to f if u belongs to this local SOAWAL space and it satisfies this integral equality for every state function. Okay, so basically if a classical solution exists, then it is immediate to see that classical solution is a weak solution. Okay, so this is how the notion of weak solution generalizes the classical solution, the notion of classical solutions. Okay, so let us take a quick example here to understand the weak solution. Okay, so again let us consider our we are in the setup of real line. You consider the domain is basically open interval minus 1 comma 1. You consider f is the basically step function, and in this case your PD is basically nothing but a second order body, and excuse me, and I am considering the problem basically the delay problem. Basically u is vanishes on the boundary, and you already know that this problem do not possess a classical solution. Now the question is whether this problem has a solution in the weak sense. So for that, what do you have to do? We have to find a function u which in the SOAWAL, which belongs to the SOAWAL space, and it satisfies this integral inequality. Okay, for every state function phi coming from this space. Okay, and how we have obtained this integral equality? Basically we have applied the integration by parts formula here again. Okay, now let us see how we can find such a function u. So for that, what we do is that we solve the problem in the two sub interval minus 1 comma 0 and 0 comma 1. Okay, if you solve this problem in separately in these two sub interval, then your solution will be precisely looks like this, and we have obtained this solution using the fact that u is in C1. Basically derivative is continuous. Okay, now if you look at this expression of this function u carefully, then you can see that derivative of u is basically x plus half and minus x plus half. Therefore u prime is no more one times differentiable. That is why the function what we have obtained here u is not in the class of C2, but it is in the class however it is in the class of C1. Okay, therefore the function ux here is not be will not be the classical solution, but it will be a weak solution of the PDE. Okay, so to show the weak solution of the PDE, what do you have to show? So first we have to show that the function must belong to the right SOAWAL space. That is the first condition, and second condition is that it must satisfy this integral equality. Okay, so basically for that, what do you do? Here is the problem point is 0, right? So we consider the domain by removing the point origin by considering in the positive epsilon. Now in this domain your function u is basically the classical solution because here 0 is not there. Okay, so now you apply the integration by parts formula, then you are left with these expressions. Now the final job is to pass the limit in this expression. So you can able to pass the limit in this expression by using basically the Lebesgue dominated convergence theorem, and finally you will have this expression which claims that the function what we have obtained here ux is a weak solution of this PDE, and it is in the class of C1, it is not in C2. Okay, so that is how the weak solutions is basically defined, and here is this is how the we can find the weak solution of some PDEs. So here is one existent results of weak solution. It says that if the given function f is in the class of L2, then there exists a unique sorry, not unique because I am considering locally. So there exists a weak solution in the local SOAWAL space to this PDE. Basically you can prove this existence of weak solution by applying direct theorem of calculus of variation. What it says, basically you have to show that this energy function is coercive and weakly lower semi-continuous and bounded from below. Then this function achieve minimum, and that minimizer will be the solution to this PDE. Because if you do the Frechet derivative of this functional, then the Frechet derivative is nothing but the weak formulation of this PDE. Okay, so these are the things about the weak derivatives and existence of weak solution. That's all. Okay, so now let us move to the nonlinear version of Laplace operator. So far, what we have seen, that we have considered the Laplacian u equal to f. Now we will consider a nonlinear problem. Basically, the p Laplacian u equal to 0. Okay, here p is basically lies between 1 to infinity, and it is fully nonlinear problem. Okay, here we say that u will be a weak solution to this PDE if this integral condition satisfied for every test function. Okay, and u should be belongs to this local SOAWAL space. And one important remark here is that we obtain this expression by multiplying test function to this PDE and again applying the integration by parts. So formula. So basically we are applying integration by parts to obtain the weak formulation of the PDE. This is basically, it's called the weak formulation of the PDE. Okay, so moreover, if the weak solution is continuous, then we call the weak solution as a p-harmonic function. Okay, so here is the one existence result. It says that there exists a unique weak solution to the Dirichlet problem minus p Laplacian u equal to 0 and u equal to g on the boundary. Now, what about the regularity of weak solution? De Benedetto and Lewis proved that weak solutions are in fact in the class of C1 alpha log, which means weak solutions are in fact C1 and derivative are in fact Holder continuous. Okay, this is the meaning of C1 alpha log. Okay. Now, as I told you, our main aim is to discuss the super solution, basically the weak super solution. So what is the definition of weak super solution? So here is the definition of weak super solution. We say that U belongs to this local SOAWAL space is a weak super solution of the PDE minus Laplace p Laplacian u equal to 0 if this integral is non-negative for every non-negative test function. Okay, so basically why we need this kind of assumption that U belongs to the local SOAWAL space. Basically, if U belongs to this local SOAWAL space, then this integral exists. That is why we are taking this assumption in the definition of weak super solution. Okay, but converse not true. Okay, if U belongs to this space, then this integral makes sense, but converse may not be true. Okay, because I will see in a few examples here. So because if you consider here the fundamental solution, we have seen the fundamental solution for the Laplace equation, right? So for the p Laplace equation, this is especially the fundamental solution. Okay, it is basically the generalizing the fundamental solution to the linear case to from the linear case to non-linear case. Okay, now if you see here for the case when p is strictly less than n, the fundamental solution has a singularity at origin, right? So therefore if this fundamental solution is a continuous weak solution of the PDE in the domain where the domain does not contain the origin. Okay, so if the domain contain origin, then your fundamental solution fails to belongs to the right SOAWAL space because this integral is infinity and it fails to belong to this right SOAWAL space. Therefore, it is not a weak solution and hence it is not a weak super solutions. Okay, however, if you truncate means if you consider the minimum of phi and k for every positive k positive integer, then they are belongs to the correct SOAWAL space, means this SOAWAL space, and they are weak super solution. Now the question is, what is this limit of this truncation function? Limit is precisely phi, the fundamental solution. Okay, so therefore what we have seen in this example is that increasing limit of weak super solution may fails to be a weak super solution. Now the question here comes, what will be the closure of weak super solution under this increasing limit? Okay, and the answer is basically p superharmonic function. So we say that a function v belongs to V is basically defined on the domain omega. It may include, it may achieve infinity. Okay, is said to be P superharmonic in a domain omega if it is lower semi-continuous and finite in a dense subset, and it obeys the comparison principle for every relatively compact relatively compact domain, compact subdomain. Okay, so what do you mean by that? Basically, if you take H is a p harmonic function in the subdomain D, and H is less than equal to V on the boundary of the subdomain D, then H must be less than equal to V inside the domain. This is precisely the comparison principle. Okay, it should obey here. Okay. Now, one important example of this class of p superharmonic function is precisely the fundamental solution phi x, and there are many more. For example, the Newtonian function. Now, if you want to see this function basically geometrically, uh, uh, so let us think in the one variable case, in the real line case. So basically, p harmonic function in real line are just the line segment. Okay, and your comparison principle tells you that p superharmonic function are basically exactly concave function. Okay, so basically it's look like this type of pictures. Okay, and in several dimensions also the concave function are also p superharmonic. Okay, now one important observation here is that we have not assumed any kind of regularity in the definition of p superharmonic. Okay, only connection through the PD is by basically the this comparison principle. Okay, now if you assume the enough regularity, like if the p superharmonic function is continuous and it belongs to the local Sobolev space, then your p superharmonic function is nothing but weak supersolution. This means it satisfies this integral inequality. Okay, and converse also true. Now the question is, what will be the in general connection between p superharmonic function and weak supersolutions? Okay, so here is the result which I wrote it in the two cases. First one is bounded case and second one is unbounded case. Okay, let me see how much time I have. Okay, 10. So basically, if you have a bounded p superharmonic function, then the bounded p superharmonic function, in fact, uh, uh, basically impact in the locally Sobolev space, means with gradient exists and it belongs to the local Sobolev space, and moreover it satisfies this integral equality, means every bounded p superharmonic functions are weak supersolution. Now what about the unbounded case? For unbounded case, what happened here is that if V is a p superharmonic and it is unbounded, then we can prove the higher integrability. Basically, V belongs to LQ log when Q belongs to, Q is basically less than this number, and weak gradient exists, and weak gradient belongs to LQ log whenever Q less than this number. Okay, so basically, what happened here is that we are not claiming that the p superharmonic function V is belongs to a Sobolev space, but we are claiming that its weak gradient exists and weak gradients belongs to LQ log. Okay, for the case when p less than still less than equal to n. Okay, but if p bigger than n, in this case, for the case when p bigger than n, in this case your weak gradient is basically belongs to LP log, and hence it is belongs to the local Sobolev space. So for p less than equal to n, it does not belongs to, it may not belongs to weak Sobolev space, local Sobolev space, but for p bigger than n, it belongs to the local Sobolev space. That is the meaning, and moreover, it satisfies this integral equality. Okay, so this is basically the case for the unbounded case. Basically, the case for the unbounded p superharmonic function. So what it says basically, it is weak gradient exists and it satisfies this integral inequality. Okay, that is why we say that p superharmonic function are generalizing class of weak supersolution. Okay, for example, your fundamental solution phi, what we have seen here, basically this fundamental solution phi. So for p less than n, it does not belong to local Sobolev space. Okay, but it satisfies this integral equality. Okay, so that is why we say that p superharmonic functions generalizing class of weak supersolution. However, for p bigger than n, if you take here p bigger than n, then there is no singularity. So in this case, your fundamental solution belongs to the right SOAWAL space, and it is in fact a weak solution, and hence it is a weak super solution. So this is basically the result for the p Laplacian equation. Okay. Now let us move to our original problem, which is basically parabolic p-Laplace equation. So basically, we are considering here the parabolic p-Laplace equation in the cylindrical domain omega t. Omega t is basically nothing but it is a product with the space domain omega with the time interval. So now our domain is basically bounded. So here what we have basically the parabolic boundary. Okay, so how the parabolic boundary is defined? Basically, parabolic boundary in picture, basically if you think a cylinder, it consists the lower part of the cylinder and the lateral part. Okay, so this is basically the parabolic boundary we are considering. We are not considering the upper part of the cylinder. Okay, because we can take capital T, can be anything. It can be goes to infinity. Okay, and here also we need some notion of space-time box. Basically, space-time box is basically nothing but it is a product with the rectangle in the space with the time interval. Okay. Now, what will be the solution space to this PDE? Okay, that is first important thing we should have. Okay, so basically here we will consider the parabolic SOAWAL space, which is basically given here as a solution space to our PDE, and it is basically consist of all function u x comma t. If you fix t as a function of x, it belongs to the SOAWAL space, and if you fix x as a function of t, it belongs to the LP space, and it is a Banach space with respect to this norm. Okay. Similarly, you can define the local parabolic SOAWAL space. Okay. So now here is the definition of weak solution to the parabolic p-Laplace equation. It says that U is said to be a weak solution to this PDE in this cylindrical domain omega t if U belongs to this local parabolic SOAWAL space and it satisfies this integral equality for every state function. Okay, so again I want to remark here that we obtain this expression by applying the integration by parts formula. Okay, so similar to the p-Laplacian case, if the weak solution is continuous, then here we call the weak solution here as p-caloric function. Okay, and similarly we can define the weak super solution if this integral is greater than equal to 0 for every non-negative state function, and similarly we can define the weak sub solutions. Now here one important remark is that for p lies between 1 and 2, our problem is basically singular. Okay, so in this case we divide our problem into two types. One is supercritical type and another one is subcritical type. Okay, so subcritical type is basically depending on if p is less than this number, n over n plus 1, then we call the problem is of subcritical type, and if p is bigger than this number, we call the problem as supercritical type. There is a reason why we are calling the subcritical and supercritical type. So I do not have so much time, so let me go to the results. So basically, what are the regulatory results? The regulatory result says that the weak solutions are in fact locally Holder continuous here for the parabolic p-Laplace equations, and for the case when p is bigger than this number, weak solutions are in fact locally bounded. Okay, but for if p less than this number, then there exists unbounded weak solution. There are certain examples you can find in this Bhubaneswar and Bhubaneswar et al. The papers. Okay, and moreover, if in the similar notion, if you truncate basically the super solution, then the truncation is also a weak super solution. Okay, and one important remark here is also that in the definition of weak solution, weak super solution, we have not assumed any regularity in time. You can see here you have u del t phi. We have thrown the derivative of ut to the derivative of phi by applying the integration by parts formula. Therefore, this step function 0, 1 in the time variable is a weak super solution. Okay, and similarly for the case of p-Laplace equation, like the fundamental solution, here we do have the fundamental solution for the parabolic case, which are known as the Barn-Blatt type solutions. It has these expressions for p lies between this number, and for p bigger than 2, its expression is basically looks like this. It is complicated, however, this is a fundamental solution for the parabolic p-Laplace equation. Okay, but one thing in the common here is that Barnblatt solution and the Barnblatt type solution, both the functions has singularity at origin. Okay, therefore the Barnblatt type solutions or Barnblatt solutions is not weak super solution in any open set containing origin, because it fails to belong to the right Sobolev space. Okay, because we need in the definition of, we have imposed that in the definition of weak super solution that the weak super solution must belong to the local parabolic Sobolev space. Okay, therefore the fundamental solution, which is here, is basically the Barnblatt solution, is not in the class of local parabolic Sobolev space. But if you truncate it, then there belongs to the correct Sobolev space and there weak super solution. And similar notion here is that an increasing limit of weak super solution may fail to a super solution. Here is the example. Okay, so limit is basically the Barnblatt solution, and Barnblatt solution is not a weak super solution in any domain containing origin. Okay, therefore, what will be the closure of this sequence of weak super solutions? Okay, and here is basically the p super here we have basically p supercaloric function. It is defined similarly in the similar fashion like in the elliptic case. Only different here is the comparison principle. Here the comparison principle is basically the obeys on the parabolic boundary. Okay, so basically it obeys the parabolic comparison principle in each space-time boxes. Okay, and everything is remains same. Okay, so as an example, you can see that Barnblatt type solution is a supercaloric function, p supercaloric function, but it is not a super solution, and there are many more. Okay, now let me few results related to the connection between the weak super solution and p supercaloric functions. So here is the result for p bigger than equal to 2. So for p bigger than equal to 2, Kinnunen and Lindquist proved that every bounded p supercaloric function is in fact weak super solution. And for p bigger than 2, and if your p supercaloric function is unbounded, then there are two mutually disjoint class. One is Barnblatt type class, and another is basically complementary to Barnblatt type class, depending on if it belongs to LP log, this LP space, L log p minus 2. If your unbounded p supercaloric function belongs to this space, then it is in fact locally integrable and Sobolev gradient exists, and it satisfies this integral inequality. Okay, and if it does not belong to this LP space, then there exists a time slice where the function is precisely infinity. Okay, so here is the different from the elliptic case to the parabolic case. Okay, for the unbounded case, basically for the unbounded case, these supercaloric function belongs to two mutually disjoint classes. One is Barnblatt type, and another one is complementary to Barnblatt type. Okay, this is the difference between elliptic and parabolic case for the case when p bigger than 2. Okay, and one example to this class is basically precisely here, this function ux over t minus t naught to the power 1 over p minus 2. This function is basically p supercaloric, and it belongs to this complementary class of Barnblatt type. Okay, now let us go for the case when p lies between 1 and 2. Basically, let us move to the case of singular case. So in this case, what we have proved is basically that for the bounded case, we have proved that the result is true for the full range. Basically, we extend the result for the case p bigger than equal to 2 to the entire range. And we have proved that for the bounded case, if u is a bounded p superharmonic function, then it is a weak super solution. However, for unbounded case, we can able to prove the result only for this range. If p bigger than this 2n over n plus 1. So that is why we divided our problem into two cases: supercritical case and subcritical case. And this is basically the supercritical range. What is the benefit of taking this supercritical range? Basically, if p bigger than this number, n over n plus 1, by applying the embedding result, we have L2 integrability that we have used here. Okay, so basically the first result says that if u belongs to the p supercaloric function belongs to this magical LP space, then it is we have the higher integrability and weak gradient exists, and it satisfies this integral equality. Okay, and second thing is that if, which is basically the complementary class, if it does not belong to this magical LP space, then the p supercaloric function has a singularity in the space domain. Okay, so basically there is a point x naught in the space domain where the function is precisely infinity. So here is the different for the case when p bigger than equal to 2. So for p bigger than equal to 2, what do we have? We have singularity in the time slice. For p less than 2, we have singularity in the basically in space. So that is the different phenomena we are observing here. Okay, so one example we have also obtained here is basically in this class is basically this function, this u infinity function, ct over mod x power p. So this function is basically, you can see that it has a singularity in the space, which is specially at origin, and this function is p supercaloric. And second thing is that it is not a super solution in any domain containing origin. And third thing is that it does not belong to this magical LP space, basically L log n over p 2 minus p. Okay, so basically it u infinity doesn't belong to this any LQ whenever q belongs greater than this magical number. So these are the different phenomena we have observed in the case of when p bigger than this number 2n over n plus 1. Basically, we have extended the result for the supercritical case. Okay, for the subcritical case, it is still open, and if basically if someone is interested, you can try, and I am also personally trying. So that's all I wanted to say, and I think I am over 5 minutes. So thank you. Yes.
May I ask you one question, Dr. Giri?
Yeah.
Okay. So thank you for your beautiful talk. Like I heard you after so many days.
Yeah.
So I have one doubt. Like from you studied the super solutions of parabolic equation, parabolic p-Laplace equation in one
Mhm.
cylindrical domain. So
Yeah.
you have considered one space domain omega. So my doubt is that is there any restriction on the that space domain for
No, no. There
finding
is
solution?
domain means it should be open and connected. That is enough.
Okay, okay.
So
And okay, thank you. And one more doubt, like we study, there is motivation behind studying weak solutions. So can you explain me the motivation behind studying weak super solution? Why we are studying super solutions? Like if we are unable to find the solutions, or can you
yeah,
explain it?
actually, super solutions are basically the more generalized in class. Okay, and sometimes
Yes.
basically there are a lot of applications behind the super solutions. Okay, so sometimes we are not able to show whether this problem has a super solution or not. Okay, sorry, solution or not. Okay, so in this case we can talk about the super solutions, and moreover what we have seen here that if we have some kind of function which is lower semi-continuous and it obeys the comparison principle, then you can directly say that it is a weak super solution to this PDE. That is one benefit. You no need to check by the definition. If you have some function which is lower semi-continuous and finite in a dense subset, and it obeys the obeys the parabolic comparison principle, then you can directly say that it is a weak super solutions for the bounded case at least. For the unbounded case, it is basically you have different kind of things that you have that I have discussed here. Okay, so this is I basically why I am studying this. Basically, I say that from the theoretical point of view, and there are many applications. You can look at the book of basically the Chinese author books. It's basically the Chao. There are some applications related to that also.
Thank you so much.
Okay,
Thank you so much.
welcome.
Anyone else? So I don't think anyone else has any question. Anyway, if anyone else has any question, you can connect to Dr. Giri afterwards to get the clarification. So thank you so much, Dr. Giri, for accepting our invitation and presenting such a wonderful talk on this topic. So I think those who are listening to you carefully must have benefited from this nice presentation. Thank you so much. And
Yeah, welcome,
thank
welcome.
you everyone. And now I request our Dr. Sai Gopal to offer the vote of thanks formally. Dr. Sai Gopal.
Yeah, thank you, thank you. Yeah.
Thank you. Thank you, Dr. Giri, Dr. Sai Gopal, and Dr. Akasmika Panda. Thank you, everyone.
Yeah.
Thank you. Let- yeah.
Okay.
Thank you.